Hello, this is my introduction to dynamic programming, and right now we'll be going through a sample leak code problem that can be solved using dynamic programming just to show off how to approach these type of problems. So the problem that we're going to be going over is the house robber problem from leak code. And in this problem, the constraints are your professional robber planning to rob houses along a street, and the only restrictions you have is that you cannot rob two adjacent houses. So we're going to be given a list of the money values at each house, and we have to return what's the maximum amount of money that we can rob in the entire row of houses. So here's a sample of what a input could be. So this is a row of 5 houses, and each of the houses have certain money value attached to them. So at the start, one naive approach to the problem might be just to attempt brute forcing the problem, which in this case is calculate all of the combinations of houses that you can rob, and then calculate the amount of money robbed from each one to find out which one is the greatest. So in this problem space, that's actually not too bad since there's only 5 houses, and we can see that the set 135 is going to give us the maximum amount of 12. But as problem sizes are increased, this algorithm actually is not very inefficient since it's going to be done in almost factorial complexity, which is probably not going to be accepted as a solution on the leak code problem since it's very slow. So we need to find out a way to improve on this brute force approach. So currently what's been happening in the brute force approach is that we've been considering all the combinations and then we've had to calculate a total for every combination. And looking to avoid that, we can try to implement a method that gives us the exact maximum amount of money that we can get at a house location. And what this means is at every point that we get to in the algorithm, we'll always know what the optimal amount of money robbed up to that point is, and we can use those previous calculations to calculate the next point and on until we get to the end of the house. Right. And what this gets us into is making an optimal choice at every position in the house row. So at every house, we can choose to either rob it or skip it. And those are the only two cases when we get to each point. And those cases are dependent on previous choices, which is to say that if you're at a point and you have to choose it, you cannot choose it if you've robbed the house before because of the adjacent houses restriction. So what this gets us into is there's two possible ways to get an amount of money robbed at house 3, right? If we rob house 3, you cannot have robbed house 2, which means it's whatever amount we've robbed up to house 1 and then added to the amount that we've robbed at house 3. Or without robbing house 3, it's the amount that we've gotten up to house 2. So we can find the optimal amount by taking whichever one is greater between those two choices, either the maximum amount at house 1 plus the value of house 3 or the maximum amount at house 2. So what this allows us to do is implement a recursive solution. So there's two base cases here, which is the first house, which we know to be the value of the first house, and the second house, which is whatever is greater between the first two houses. And then the recursive case here is when we're robbing up to house of I, we either take the max of the previous house or the maximum of the current house plus the house before the previous house. And this way, at every point in the recursion, rob I will give the optimal amount of money that we can rob up to that point. And as this is propagated all the way to the call of rob 5, we know what the maximum amount is on the 5th house and the last house, therefore finding what is the greatest amount of money we can rob in the entire row. So what this leads to is it leads to a recursion tree looking something like this, where every single recursive call is going to create 2 more recursive branches that go all the way until they terminate in the base case. And what this leads to is some exponential time in the problem, which is still inefficient because we want to reduce this to something that is polynomial time, right? So we need to find a way to optimize this recursion. And what we can notice here is that there's a lot of repeated calls to the same function. So we know that in this problem, if we call rob of 3 twice, it should always return the exact same value. So what we can do to improve this recursive call is every single time we make a recursive call, store the results so that instead of performing recursion over and over again, we're just going to be able to look up whatever the value was for the first time that we've calculated that. And this concept of storing solutions to subproblems is dynamic programming. Essentially, whenever we have a recursive algorithm, we can store the results of that recursion into a table and then avoid the overhead of making repeated recursive calls by simply just looking up the items that are stored in the table. There's two approaches to this dynamic program solution, either going bottom up or top down. So top-down approach is performing recursion and storing each result in a table for lookup. So what this means is every time that we return out of a recursive call, so say we've done rob1 and we've returned 2, that's going to be stored in the table. And as we go back up the recursive tree, each of those calls is just going to be looking at the value of the table. And then bottom up approach is iteratively filling up the lookup table using previous entries. So in this case, we're going to go in a loop from 1 to 5. And for 1 and 2, those are the base cases. So we can store them directly into our lookup table. And everything onwards from that point, all of the recursive call only depends on items that have already been filled out in the table. So we don't need to make any recursive calls, as we can just look up the positions in the table since we know they're going to be filled. So here's some sample code for the solution of this problem using the bottom-up approach. So you can see that in the bottom-up approach, we only need to store two values, which is the house that was before the current position and the house that was before that, since the recursion case that we're doing here is the maximum of the previous house or the current house plus the house before that. And what this returns is this returns the final current money, which is the optimal amount at the final house, which is the optimal amount of the whole row. So this technique can be used in many problems that require recursive solutions as an optimization technique. So suppose like we're calculating the Fibonacci numbers, instead of having to do multiple recursive calls, just like this recursive tree where there's two branches, we can just store the results of each of the recursive calls, and that'll result in an optimization. So I hope that helped understand dynamic programming a little better, and thanks for watching.